Wind is fundamentally a massive, invisible river of kinetic energy flowing continuously across the Earth's very surface. The engineering challenge is taking that chaotic, highly irregular force and routing it through a mechanical system to produce stable, usable electricity. Humanity has harnessed this kinetic energy mechanically for centuries, using traditional rotating blades to do direct physical labor, like grinding grain or pumping water. Modern utility grids require a much more sophisticated architecture. They rely on a specific machine known as a wind energy conversion system, or WEX. We will build a complete WEX from first principles to understand exactly how it works and how to accurately map its mechanics on paper. First, we must examine the physical relationship that dictates wind power, the cubic power law. This graph plots wind speed against power output, governed by a basic formula. Power equals wind speed cubed. Because of this cubic relationship, a tiny increase in wind speed yields a massive multiplication of electrical output. Doubling the wind speed increases the power eightfold. Because of this cubic relationship, every millimeter of its design, its total structural height, and its geographic placement is calculated to maximize efficiency. Before we engineer the internal machinery, we must lock down the 4 physical factors in the environment that dictate a turbine's maximum energy potential. The first factor is wind speed, which dominates output through that exact cubic formula. The second is air density. Heavier, denser air packs more physical mass per cubic meter, applying a greater direct force to the turbine structure. The third is the sheer physical size of the blades, which determines the total swept area available to intercept the wind. The fourth is the height of the tower itself. Tower height acts as a multiplier for the first factor. Building taller structures is the most reliable way to clear ground friction and reach the faster wind speeds required to exploit the cubic power law. Manipulating this physical footprint in the environment is just as critical as the components housed inside. Now we can construct the internal pipeline. The first physical point of contact in a WEX is the assembly of the rotor and blades. The wind's kinetic force strikes the pitched surface, which causes the blades to rotate. This step successfully captures mechanical energy. These rotating blades turn the main shaft. This is a heavy central axis housed inside the nacelle, the protective casing at the top of the turbine. The shaft feeds directly into a critical intermediary component, the gearbox. The massive turbine blades rotate relatively slowly. The gearbox uses internal gear ratios to step up this slow mechanical rotation into the extremely high-speed rotation required downstream. That high-speed output shaft terminates at the generator. Here, the mechanical phase ends. The generator utilizes electromagnetic induction to complete the conversion, turning that rapid mechanical rotation into electrical current. Overseeing this entire drivetrain is the controller. It constantly monitors wind speeds and can safely apply physical brakes to the system if the rotation speeds become dangerously high. The generated electricity is then routed out of the nacelle, traveling down the heavy tower structure. Once at the base, it is outputted into the regional power grid for distribution. A WEX operates as a highly linear pipeline of energy conversion, from kinetic wind to low-speed mechanical force to high-speed mechanical rotation, and finally to electric power. The internal WEX pipeline we just built must be housed in a specific structural design. Engineers classify these primarily into 2 architectures. The first, and overwhelmingly the most common, is the hot, or horizontal axis wind turbine. Its defining physical characteristic is evident in the name. The main axis of rotation is parallel to the ground. HOTs dominate modern infrastructure because they offer the highest aerodynamic efficiency, allowing operators to capture the highest possible returns from the cubic power law. The alternative architecture is the VOT, or vertical axis wind turbine. In a VOT, the main rotor shaft is oriented vertically, perfectly perpendicular to the ground. This setup creates an inherent engineering trade-off. It boasts a simpler design that doesn't need heavy yaw mechanisms to constantly pivot and face the wind direction, but it suffers from significantly lower overall energy efficiency. Engineers have historically experimented with various structural combinations, adjusting blade counts and utilizing lattice towers to solve these trade-offs. The choice between a hot and a watt is a strict calculation balancing maximum potential energy extraction against mechanical complexity and maintenance costs. Moving past the mechanics, we must look at how these systems impact society. The operational advantages make it highly desirable. Wind is a renewable, clean, and entirely free source of raw material, resulting in exceptionally low operating costs once the machine is built. These systems power remote grid networks and provide localized solutions, including standalone water pumping, industrial battery charging, and rural electrification. But we must balance these benefits with strict operational disadvantages. Wind availability is inherently irregular. The machines require massive initial capital costs. They generate mechanical noise, and utility-scale farms require large tracts of land. Wind energy is an essential, highly economical tool, but only when deployed in the correct geographical contexts, where its output reliably outweighs its physical footprint. Understanding this system intellectually is only half the process. True technical proficiency is demonstrated through the ability to reproduce its logic clearly. A comprehensive technical explanation requires a specific framework, the definition of the system, its working principle, a list of internal components, the advantages and disadvantages, and its practical applications. The most effective way to communicate this system's architecture is through the WEX schematic diagram. This 2D block diagram perfectly illustrates the system on paper without complex 3D sketches. Energy flows from the wind hitting the blades, turning the shaft, stepping up rotation in the gearbox, inducing current in the generator, and finally exporting to the grid. Mastering this single diagram proves a complete structural understanding of how humanity engineers machines to turn thin air into electric power.